I'm Madhu. I'm a clinical associate professor at Nottingham. I spend half my time as a pediatric oncologist in Nottingham Children's Hospital and half my time at the University of Nottingham. I'm one of those people who is cancer agnostic, as in I don't have a cancer of interest specifically. I'm more interested in putting tumours on a diet. So although this says, can we starve them to death? The idea is to see if we need to find out what each tumour type eats or what nutrients they rely on and whether we can harness that. And hopefully I've got some examples. It's not an original concept, but it's understudied. And certainly the leukemia guys are slightly ahead of the game, but they've got it slightly easier compared to the solid tumor guys because their cells are discrete and flowing in the bloodstream. People with lumpy, bumpy tumors have it slightly harder. So why is this important? Why do we need to know about this? And this boils down to what a cancer cell is. So if we look at normal versus cancer cells are bigger, nastier, grow uncontrollably, look very different to normal cells in that part of the body. And we all know this. Now, about 20 years ago, these guys, Hanahan and Weinberg, wrote this seminal paper on what makes a cell cancerous. It's not just how it looks under the microscope. A cancer cell can hide from the immune system. It can sort of be a parasite, if you like. It is immortal, and so on and so forth. It can make its own blood vessels. Particularly a solid blob can make its own blood vessels. So in some ways, it's like something growing within a normal person, a little bit of like an alien sitting inside your body, if you like. And it has replicative immortality. And they started off with these 6 principles of what characterizes a cancer cell or what makes a cell cancerous. About 20 years later, they decided, well, there's a lot more going on than just that in a cancer cell. And they modified their criteria. And I just want to draw your attention to the purple bit at the top that says deregulating cellular energetics. And what that basically means is it hijacks the cell's mechanisms and it uses up all the goodies in the body. I know we hear a lot about genome, and every time you sit in a consulting room, they'll go and say, we've genome sequenced your tumor and produce a list of things. Sometimes we know what those genes mean. A lot of the time you get a readout that's like one of my consultants used to use the analogy of all the genes in your body are like the entire text of the Bible. And if you think every time a cell reproduces itself, it's got to rewrite the whole text without a spelling mistake. How's that going to happen? So a lot of the time we find genetic abnormalities, they don't really mean very much in terms of how that changes a cell. They don't also mean very much to us in terms of, so what can you do about it? We don't have drugs to treat every mutation. So I'd like to draw your attention to the fact that when one cell has to become 2, it not just doubles its DNA, it doubles itself. It doesn't just clone the gene code. It doubles the amount of organelles in it. So it's almost like having a baby, but a full-sized baby like you. So there's a lot of growing that needs to be done. And that's a pretty exhausting process in terms of how much energy that consumes in the body. And I've just got this here. You don't have to look at it. It's a sciencey slide. I'm just drawing your attention to the fact that if you've got lack of nutrients during cell division, during that growth phase, which is green there and orange there, the cell just commits suicide. So autophagy is the cell eating itself. So it just gets stuck and it dies. And this is sort of an understudied thing. I kind of got into it. I've circled the thing in black. That's what I did my PhD on 10 years ago. And it's like this master energy switch that When the cell's energy mechanism is going to overdrive it, it's the brake. It's the brake mechanism. And tumor cells hijack that brake mechanism. So there are ways in which we can try and target the vulnerability of the cancer cell that has to cut corners. If a cell is growing that rapidly, then like the hare and the tortoise, you know, the hare starts off galloping away, whereas the tortoise is the normal cell trying to slowly divide. It chugs along, whereas the cancer cell, then errors accumulate. So at some point, there are points where you can interfere and stop that process. Cancer cells also don't invest in everything. If your only purpose in life is to make more copies of yourself, you wouldn't invest in things that would stop you growing or make it harder for you to, you know, like, it's like if you took steroids rather than went to gym and worked out for 6 months or something. It's like that. So they take shortcuts. And also, sometimes they get addicted to certain chemicals. So I've got that. I didn't want to put a very risque picture as a child dipping its head into a chocolate egg. But it's just the fact that the tumor will be addicted to something. And sugars are a good place to start. So there are all sorts of nutrients that cancer cells utilize differently. And a normal cell has a slower process we call oxidative phosphorylation. It's a slower process of using the sugars in the body, but it generates more energy, but it's more long-winded. So the cancer cell doesn't want to do that. Instead, even when there's oxygen, it will use a shortcut process to just make more energy quickly. It's not a very elegant process, but it does the job. And that was identified in the 40s. It's called the Warburg effect. We've known about it for donkey's years. We study it, but we don't do anything with that information at the moment. If you look at fats, again, this is ovarian cancer, but it could be any old cancer. So the cancer cells shunt a lot of fats into them. And again, they hijack fats into making more sugar. And if you look at proteins, which is my hobby horse at the moment. So proteins is a network. Sorry, it doesn't project very well, but nobody's going to read that anyway. So proteins are necessary for everything. So these are the common food groups. And if you think about the amino acids, of which there are 20 in the human body, they're just like bits of Lego. And you can build a tank, you can build a car, you can build a whatever. So you can make any number of proteins. So there are certain amino acids that I've circled, which again are either known about or I'm interested in. And my work is all about can we use these differences that we know happen? And we already do. So it's not like what I'm talking is rocket science, but it's just something we need to do more of. So this is an example of an amino acid called asparagine. And those of you who've had children who've had leukemia treatments have heard of this drug called PEG, or PEG asparaginase. It's given in the leg, it's an injection, kids hate it. But what that does is it depletes this amino acid in the blood that the leukemia cell is addicted to. And if you don't give it enough, it can't make its own. It doesn't have the mechanism to make its own. So it relies on what comes from the outside. And if you cut that off, the leukemia cell dies. And they've been using PEG for well over a decade. It's a well-studied drug. But we're not using it for anything other than leukemia at the moment. And it's probably because this amino acid is specific to leukemias. But there are other such targets that we can look at. And if we can look at things like that, we can have kind of less toxic treatments and you know, hopefully something that won't interfere with the growing child. Again, I've got two examples of the work that I'm doing at the moment. The first one is to do with brain tumors. Now, that's an old slide. So all cancer survival is that yellow line. It's above 80% now. And you can look at other than so-called benign brain tumors, and I would challenge anyone who calls any brain tumor benign, because they're all bloody nasty. You can see some have dismal survival, 2 in 10, and so on. And the reason is we can't get drugs into the brain, okay? It's very hard to get drugs into the brain because there's something called the blood-brain barrier. It's like this wall that stops chemotherapy getting into the brain. But if we could, like the leukemia story, pull out all the goodies from the bloodstream, so nothing, we can deprive the brain tumor of the goodies, then that's a much more elegant way of circumventing the blood-brain barrier. So we looked at this amino acid called arginine, and it could be anything, okay? Just think chocolate. You have to go to Tesco's, you have to buy the chocolate, get it into your house, and you have to eat it, and you have to process it. And if you didn't have chocolate in your house, and you were crazy like me, you would melt butter and sugar and cocoa and make it inside your house. Now, if you didn't have the butter and sugar and cocoa, you wouldn't be able to make chocolate unless you bought it from Tesco's or Aldi or some other supermarkets are available. So this is a slide which looks at, can the cell take up arginine? Can the cell use arginine? And can the cell make its own arginine? So we've got a whole range of brain tumor cells. We stain for this panel of arginine pathway enzymes. And the highlight is that you can look at any type of brain tumor. This holds true for about 5 or 6 different types of brain tumors. I've only got one up here. But they cannot make their own chocolate, okay? They can allow chocolate to get into the cell. And they like eating chocolate. And they like eating, there's a specific enzyme that chews up the arginine, okay? And that's different in brain tumors compared to the rest of the body. It's a different isoform. So people have tried arginine depletion in brain tumors and shown it doesn't work, but they've targeted the wrong enzyme. The enzymes that we currently have on the market are ARG1 inhibitors. So they've kind of thrown the baby out with the bathwater prematurely, but there is further work to be done. And CRUK Horizons has got a specific ARG2 inhibitor that I'm considering working with in different types of brain tumors. The second example, because I think I'm slightly getting to my time, is liver tumors. Now, I like strangely working on liver and brain tumors because they are the powerhouses of the body. So the liver utilizes all the nutrients or processes all the nutrients, and the brain is just the organ that consumes the most energy in the body. So they're very interesting to study. Now, this is liver tumors. They are extremely rare. 1 in a million kids gets hepatoblastoma. There's mixed outcomes, so you can look at different types of risk. So if you're high risk in the yellow line, you do badly. If you're low risk, you universally survive your cancer. And we have some drugs, but they usually weaken your heart or make you go deaf. So whilst we cure these children, it's a big price to pay, and half of them end up getting a transplanted liver as well. There's no targeted therapies for this, and the drugs that we use are about 20 years old. Now, I won't go into the details about what we did, but we basically took normal liver and tumor liver from the same blob of liver that they take out. So they take out part of the liver when the child undergoes surgery for hepatoblastoma, or sometimes they take out all of the liver and do a transplant. So you can see diseased parts within the liver and non-diseased parts within the liver, which are labeled as non-tumor and tumor. And then we grind it up with a pestle and mortar, elute all the goodies, put it through a very sophisticated machine, and then it gives you a list of about 1,000 chemicals that come out of that soup that we've analyzed. And unsurprisingly, there are around 30 to 40 chemicals that are different in the tumor bit of the liver compared to the normal liver. And that's represented with all the squares being on one side and all the triangles being on the other side. It just says they're very different to one another. That's not surprising. But what is surprising is how few chemicals are responsible for this change. 30 is quite a small number to work with. And the vast majority of them are fatty acid